Hello, my name is Isaac Lara and I'm an applications engineer supporting position sensing products. In this video, I will discuss how to perform parametric sweeps on the TI Magnetic Sense Simulator TIMSS. Parametric sweeps allow users to run a series of simulations where TIMSS parameters can be set as variable values. The parametric sweep can override some of the parameters set in the simulation environment to simulate each individual scenario or combination of scenarios to accumulate resulting data across several variations. The parametric sweep function can be extremely helpful since it can help users run through various combinations without having to manually alter the values for each simulation. This feature can also be particularly useful when assessing the effect of system tolerances on a device or a mechanical configuration and magnet selection by helping users iterate through magnets to see what magnet specs would work for your system. Parametric sweeps in TIMSS can be accessed in the simulation environment during either the input or output stage of a simulation by clicking the icon on the left side of the screen. Once the parametric sweep button has been selected, a screen with the option to add a new parameter should appear along with the option to run individual sweeps or combinational sweeps. Choosing the individual sweep option will simulate the added parameter individually, allowing users a total of 250 parametrized simulation points, while a combinational sweep combines all the selected sweep parameters in a nested fashion. Up to 3 parameters can be chosen at a time, and in this mode, a maximum of 125 simulation points are available. When selecting to add a new parameter, TIMSS will provide the option to select which parameter you would like to sweep through, along with the option on how to sweep through the selected parameter. To step through values, a selected range could be given with the predefined step function between steps, or if you'd like to traverse a specific set of configurations, then a discrete set of values could be entered into TIMSS as comma-separated values. Here's an example of a mechanical configuration along with magnet details that will be used for a parametric sweep simulation on TIMSS. Feel free to pause the video to review the configuration in more detail. For this video, we will be performing 2 examples of parametric sweeps. The first will be to determine what type of magnet material may be suitable for our application. The second sweep will be used to sweep the X and Z direction in order to find an ideal offset and air gap for the sensor in both the X and Z directions. First, I will set up my baseline simulation. In this case, I will select rotation for the function type, and then we'll use a ring magnet for this example. For the sensor, I will pick a 2D Hall effect latch that will simply be used for encoding applications. The device will be a TMAG5110. With all of the inputs selected, we're ready to start configuring the simulation. We will increase the pull of this magnet to 4 poles. We'll select an aluminum, nickel, and cobalt Alnico LN9 magnet, but we'll change the outer diameter to 11 millimeters and the inner diameter to 4 millimeters and a height of 3.5 millimeters. We can start by altering the magnet's position by moving the magnet 1.75 millimeters in the Z-axis and leaving the X and Y at the default 0 millimeters. I will leave the arc length for the path of rotation about the Z-axis as 360 degrees. Next, we will click the sensor specifications dropdown to set our sensor to the right variant of TMAG5110. We would like to sense in the X and Y directions, so we will choose the TMAG5110 A2 variant. I will use the sensor position tab to set the sensor's placement. The Y will remain as 0 millimeters. For the X and Z locations, we will set the X at 7.5 millimeters and Z at 2 millimeters. Keep in mind that TIMSS uses the center of the package and the bottom of the package as reference points for the position. Finally, I will set the angular step size to 0.25 degrees. I can quickly simulate just to see what my simulation results look like so far. Looking at the magnetic field density plot, we can hide the magnitude and Z component of the field since our sensor will not use this data. Our X portion of the field does not look very sinusoidal, which can typically lead to errors in the switching points for incremental encoding. The goal for our first sweep will be to use the parametric sweep function to try to identify if our magnet's suitable for our application, and the second sweep will be used to find a more optimal placement for our sensor. Now that our baseline simulation is complete, we can continue with our parametric sweep. Since we would like to alter a single parameter, we will select Individual Sweep and then click on Add New Parameter. Here we would like to select the magnet material. Since I am not sure which magnet material may be best, I would like to go through all of them and choose the first grade on the drop-down for each magnet material. For the first one, we will select Sintered Neodymium with a grade of N35, then select Add More to enter another material. We are going to repeat this until all the materials have been selected, and we should have 6 in total. One thing to know is if you know what material you would like to use, but are not sure what grade of the magnet might be the most appropriate, you could always select a single magnet material and click on Select All to simulate all the different magnet grades available in TIMSS. Looking to the results of our sweep, we can see that the magnetic field experienced by the device greatly varies based on the selected magnet grade and material. Starting with the x-axis of the TMAG5110, the rubber is the weakest magnet that we simulated. If we isolate the rubber magnet's result, we can see that it's still capable of generating a field of up to plus or minus 15 millitesla, which is more than enough to trigger the BOP and BRP thresholds of the TMAG5110, which are just 1.4 millitesla on our selected sensitivity. If we look at the y-axis, we can see a very similar trend as noted for the x-axis. As expected, the strength of the magnetic field varies with the material, with rubber once again being our weakest magnet. Again, looking closer at the rubber magnet in the y-axis, we can see that this magnet is still capable of reaching the BOP and BRP thresholds of the TMAG5110, since the magnet at this position generates a max field of plus or minus 14 millitesla. One thing to note is the switching for the x-axis data. Changing the magnet type does not seem to have much variation on angle where the device switches, while on the other hand, the magnet material impacts the Y output more, and as we see a larger variation between switching points. Now that we have decided that our Alnico magnet is sufficient for our current placement, let's check if we could perhaps change the placement of our sensor. Since we would like to alter 2 parameters, we will select Combinational Sweep and then click on Add New Parameter. Here, we would like to select sensor position X, and for sweep type we can select either a range of values or a set of discrete values. We will go from 7.5 mm to 9 mm in 0.5 mm increments. Then, we will add our additional parameter for the Z distance, so we will select Add New Parameter once again, and we will add Sensor Z Position. This one we will sweep from 2 mm to 4 mm in 1 mm increments. Now that we have this filled out, let's click Simulate. Since we are running through nested loops, the simulation can take a little longer than when a single simulation is performed. Once the simulation is completed, we can see both our magnetic field and expected device outputs based on each combination. If you find it hard to see a specific graph, just like in the standard simulations, we can always hide the other curves. All the data can be exported by clicking the Download button on the upper left-hand corner of the simulations. The data for each axis will need to be downloaded separately, as well as the data for each output on the device. The parametric sweep allows us to develop a better understanding of the magnetic field behavior as we move the device into different positions along the magnet. The BX field was already relatively somewhat sinusoidal, and it seems to remain that way as we move the sensor further away and higher on the magnet. For the BY field, it also seems to follow a similar trend as we move the device further and higher along the magnet. The fields start to become more sinusoidal, reducing the peaks that existed in our original position. When downloading the CSV data, each axis or output will be on a single file, and each iteration that was simulated will be separated onto a different column. For our example, we start at the BX and move our way to BY, BZ, and lastly ending with the magnitude data. To ensure that this is the best placement, it is encouraged to export CSV data to Excel, or other data processing tools in order to identify which device position may be the best suited for your application and your accuracy requirements. For more information on data processing, please watch our video on data analysis for TIMSS and learn how the data can be post-processed. To learn more about TIMSS, TI Magnetics portfolio, please review the relevant collateral listed here. To get started on your simulations using parametric sweeps, please visit www.ti.com/TIMSS, and thanks for watching.